Hello and welcome back to the IIT PAL series of lectures on mathematics. We are working on the binomial theorem and its applications, and this is going to be lecture number 5. Now, in the last lecture we were looking at a particular problem. This was our problem that we were working on. F of x is equal to 1 minus x plus x squared minus x cube plus dot 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 plus x power 16 minus x power 17, which is equal to a0 a1 times 1 plus x plus a2 times 1 plus x whole squared plus a3 times 1 plus x the whole cube plus all the way till a17 1 plus x the whole power 17. And the question was, what is a2? And first we started a brute force expansion. So, we saw that 1, the first term is equal to a0 plus a1 plus a2 plus a3 all the way till a17. Then the second term minus x was equal to a1 times x plus a2 times 2x plus a3 times 3x plus all the way till a17 times 17x. So, this was my second relationship, and then we looked at x squared term, and that was, this does not have an x squared, there is no x squared here. So, I get a2 times x squared plus 3c2 a3 times x squared plus 4c2 a4 times x squared plus 5c2 a5 times x squared all the way till 17c2 a17 times x squared. Okay, so, these were the relationships. You can write more and more and more relationships, and you are going to find that all of those relationships are going to be quite complicated and hard to work with, and then you will have to solve for a0, a1, a2 all the way till a17. So, if you write for example, the 17th equation, you will get a17 straight away, right. In fact, you will get a17 to be equal to minus 1. You can see it by observation, a17 is nothing but minus 1, fine, right. Then you work with, you try to find out a16, then you try to find out a15. It is a very long winded process, because the question is not what is a16, the question is what is a2. So, you will have to come backwards all the way from a17 to 2, and you will not have time. In an exam, this is the wrong way of doing things. Whenever you see that something is taking too much time, then you know that this is not the way the examiner wants me to work it out, right. Is there a shorter method? Okay. Then we said, let us throw in some calculus at this problem, and I wrote it up like this: f prime, which is df by dx, is nothing but 1 becomes, the derivative of 1 is a 0, minus 1 plus 2x minus 3x squared all the way 16 times x power 15 minus 17 times x power 16. So, this is f prime, but you also can take the derivative of this. A0 does not have a derivative, its derivative is 0. a1 times 1 plus x gives me just a1, a2 times 1 plus x the whole squared gives me 2a2 times 1 plus x, then I get 3a3 times 1 plus x the whole squared, 4a4 times 1 plus x the whole cube all the way till 17a17 times 1 plus x the whole power 16. Okay. So, this is also a relationship. Now, if you plug in x equal to 0, you get back the same second relationship that you had. Just notice, if you plug in x equal to 0, but what happens when you plug in x equal to minus 1? When x equal to minus 1, if you do plug in that, second term becomes 0, third term becomes 0, fourth term becomes 0, 17th term becomes 0, everything becomes 0 except for a1. So, x equal to minus 1, if I plug in, then I get a1 on this side, on the other side I get minus 1, minus 2, minus 3, minus 4 all the way till minus 17. So, that gives me the value of a 1. Do you see that? So, that was the beauty of the derivative. I did not have to come all the way backwards from a 17. Okay. So, a 1 was easy enough. What about a 2? You take the second derivative. The second derivative gave me 2 minus 6 x plus 4 into 3 x squared minus 5 into 4 x cube plus dot 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 minus 17 into 16 x power 15. This was the second derivative. And what did I get? I got 2 a 2 plus 3 a 3 times 2 into 1 plus x plus 4 a 4 times 3 into 1 plus x the whole squared plus dot 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 17 a 17 into 16 times 1 plus x power 15. And now, if I plug in x equal to 0, I get back the same original relationship that I wrote a long time back, if I plug in x equal to 0, right. But if you do not plug in x equal to 0, right, you plug in x equal to 0, you will get 2 is equal to something. If instead of that you plug in x equal to minus 1, what are you going to get? If you plug in x equal to minus 1, this term cancels, all of these cancel, all you are left with is 2 times a 2. Okay. Which means 2 times a 2 is equal to 2 plus 6 plus 4 into 3, which is 12, plus 5 into 4 plus 6 into 5. So, this was 2 into 1, this was 3 into 2, just noting it. Okay. And all I did was I plugged in x equal to minus 1 and I got a 2 straight away. So, you see the advantage of doing it this way. It is quite an easy problem. We spent a lot of time on it, but not because we wanted to spend a lot of time on it. I mean, once you do these problems a few times, you appreciate the beauty of the structure. You need to appreciate the structure of the polynomial, right, and similar problems can easily be constructed. And then once you see the problem, you immediately know that, oh, I have to do a derivative and then I have to plug in x equal to something, need not be minus 1. So, that is why we went through those motions, right. So, what is going to be a 2 finally? A 2 is therefore this whole thing divided by 2. I need to know how to figure out this gigantic sum, right. It is basically 2 plus 6 plus 12, 20, 6 into 5 is 30, right. Then the next one is 17 into 6, 42, and so on, all the way till 17 into 16. Okay. How do you do this? And what is sigma of n squared? Do you know how to do sigma of n squared? 1 plus n 1 squared plus 2 squared plus 3 squared. How do you do it? Do you know what is sigma of n? How do you do it? Write it backwards. Right, add them up, right, that gives you the result as n into n plus 1 by 2. Okay. So, sigma from 2 to 17 though. So, that is from 1 to 17, from 2 to 17 is going to be that less n equal to 1 to 1. Okay. So, this is going to be 17 into 18 by 2 minus 1, this portion, and then sigma n squared. How do you do that? How do you do sigma n squared? Okay. So, what is this sum? Do you know this? You should be knowing this if you are preparing for JEE. The result is n into n plus 1 into 2 n plus 1 by 6. Right, even if you do not remember the exact numbers, you can cross check it, you can plug in n equal to 1 for example. Right, if you plug in n equal to 1, you get 1 into 2 into 3 by 6, which is 1. If you plug in n equal to 2, then it is 1 squared plus 2 squared, right, that is 5. Your answer should come to be 5. So, n equal to 2, so 2 into 3, that is 6, goes away, and remaining 5. So, this is the correct result. Okay. So, we are of course doing from 2 to 17, and so we have to subtract out an extra 1 from the whole story. So, our result is going to be 17 into 18 into 2 into 17 plus 1, 2 into 17 is 34. So, 35 by 6 minus 1, and the minus 1s will go away, and your net result is going to be 17 into 18 into 35 by 6 minus a half, right, 35 by 6 minus a half, half is 3 by 6. So, net you have got is 32 by 6, and then cancel things out, you have got 17 into 3 into 32, and whatever that is 96 into 32, 51 into 32. Right. So, this is 2 A2, and then you have got to divide this by a factor of 2. So, your final answer A2 should be equal to 51 into 16, 50 into 16 is 800. So, this is 816. All right, little bit of calculations were required. However, the solution is not bad, it is elegant, it did not take as much time as travelling all the way from 17 to 1. Okay. So, the next example that we are going to do, and here again this is going to be an exercise in elegance, how elegant is your solution. So, the question over here is suppose you have got 3 plus square root of 5 whole to the power n. Okay, I do not know what exactly n is, and the question states that if this is equal to I plus f, where I is the largest integer, and f is less than 1, greater than 0, right, f is between 0 and 1, right. So, I is the integer part of 3 plus root 5 whole power n, and f is the fractional part, some part which is less than 1, right. So, 3 plus root 5 whole power n. I do not know what that answer is, maybe that answer is 201.75. So, I is 201 and f is 0.75. This is the idea. Okay. So, suppose 3 plus root 5 whole power n is I plus f, and this is also equal to rho plus sigma, where rho is the rational part and sigma is the irrational part. I hope you know the difference between rational and irrational. Yes, you do. A rational number is something which can be expressed as an integer divided by an integer. An irrational number is a surd, for example, is an irrational number, right. So, if you have got root 5, that is irrational, 10 times root 5 is also irrational, right, 17 times root 2 is irrational. These are not the only irrational numbers, pi, e, those are also irrational numbers, and then there are many more irrational numbers. But in 3 plus root 5 whole power n, you are going to break it up into pieces, right. There are going to be integer pieces, and then there are going to be pieces which are going to be factors of root 5. So, if you have got root 5 in it, then that is the irrational part. Okay. So, here he is declaring that rho is the rational part of 3 plus root 5 whole power n, sigma is the irrational part of 3 plus root 5 whole power n. He wants you to find, or rather he wants you to show that rho is equal to I plus 1 by 2 and sigma is equal to I plus 2f minus 1 by 2. Okay. So, this is the problem statement. The problem statement is 3 plus root 5 whole power n is equal to some integer plus a fraction, and it is also equal to a rational number plus an irrational portion. Rho is the largest rational part and sigma is the irrational part. Then prove that rho is I plus 1 by 2 and sigma is I plus 2f minus 1 by 2. So, this is our job at hand. How will you do this? Let us look at the following. Now, this I am going to pull out from my hat, magician's hat. Let us look at 3 plus root 5 whole power n, and let us also look at 3 minus root 5 whole power n. Okay. So, 3 plus root 5 whole power n is going to have 3 power n plus C1 times root 5 3 power n minus 1 times root 5. So, I am showing the rational part, irrational part, plus C2 3 power n minus 2 times root 5 squared, which is 5, plus C3 times 3 power n minus 3 times 5 root 5, and so on and so forth. Okay. So, if n is odd, then this term will appear here, the nth term will come here. If n is even, then the nth term is going to show up on this column. So, depending on, let us say n is odd, in that case the nth term shows up on this column. So, 3 power n minus 3 becomes equal to 0, 3 power 0. So, that is 1, and then 5 power integer part of n by 2 times root 5. Okay. And this one is going to be C n minus 1 3 power just 3 and the same 5 times 5 to the power integer part of n by 2. And this is if n is odd, and if n is even, then this term is not, this term is going to be on this column and this term will appear here, and you will not have the root 5 at all, because n is even. Integer part of n by 2 is nothing but n by 2 in that case. Okay. So, this is generally how it is going to expand. Now, if I did 3 minus root 5 whole power n, what would have happened? 3 power n, and then over here I would have gotten a minus sign. Then the next one, this term would have been the same, because I would have chosen 2 of the root 5s. So, root 5 squared minus root 5 whole squared is 5. Whereas, for this I would have had to choose 3 of the root 5s, which gives me minus 5 root 5. So, this would have been a minus over here, minus over here, and what you are going to find is that all of these would have come with an extra minus sign. Okay. So, this is the observation, right. So, in other words, if 3 plus root 5 whole power n is equal to rho plus sigma, where rho is the rational part and sigma is the irrational part, then 3 minus root 5 whole power n is nothing but rho minus sigma. Is that okay? This seems reasonable. Okay. In which case, all you have to do to work out rho. So, here what are you doing? You are working out rho and you are working out sigma. All you have to do to work out rho, you have to add these 2 and divide by 2. To work out sigma, you have to subtract these 2 and divide by 2, right. Is that straightforward? So, add the 2, what are you going to get? So, you are going to get 3 plus root 5 whole power n plus 3 minus root 5 whole power n divided by 2, that is rho. Is that fine? Okay. Now, this is also equal to I plus f, where I is the integer part and f is some fractional part. Okay. But 3 minus root 5 whole power n, what is that going to be equal to? So, these are all integers. So, you do not have to worry about these, and inside of this root 5, for example, right, is something more than 2, right, 2 plus a fraction. So, that fraction times C 1 times 3 power n minus 1 will give you a little fraction, some other fraction. All those fractions are going to be added, and then that will leave out a certain fraction. So, there is some fractional part, and that fractional part appears only in this set of the second terms, in the odd terms, right. So, the odd terms give you a fractional part, the even terms are just pure integers. All right. So, this is one observation. When you do the plus sign, so if you get some integer for the integer part, and then for this fractional part you get some integer plus some blue fraction. Okay. Then for 3 minus root 5 whole power n, what will you get? You will get the same integer, sorry, this should have been in blue, in green, the same big integer which is the integer part, and then over here I will have minus this integer which is the integer part of the odd terms, and then I will have a minus the same fraction, the same blue dot. Okay. Now, these are all integers, all right. So, you could call this entire thing, if this can be I. So, this whole thing is capital I and this blue dot is small f. So, this whole thing is capital I plus small f. Now, this integer portion is not really capital I, right, it is something minus something, it is no longer something plus something, but maybe it is some other integer, let us call it I 2, okay, minus the blue dot which is the fraction. Now, what is the fractional part of this? So, if I have an integer this is my I 2 and I subtract out a fraction, then the fractional part of I 2 minus f, this is I 2, suppose this is I 2, and this is your f, all right. Then the fractional part of this, first of all the integer part of this is not really I 2, it is now going to be I 2 minus 1, and the fractional part is 1 minus f, right. I am trying to draw it pictorially, right. So, the integer part is no longer the old integer, this minus this, it is this minus this and minus an extra 1, and the fractional part is 1 minus f, all right. So, 3 minus root 5 whole power n will be some other integer I 2 minus 1 plus a fraction which is nothing but 1 minus f. So, if 3 plus root 5 whole power n is equal to I plus f, then 3 minus root 5 whole power n will be some other integer I 2 minus 1 plus a fraction which is 1 minus f. All right. Now, let us do some jugglery. 3 minus root 5, if you think about it, 3 minus root 5 is a value which is more than 2, but less than 3. Root 4 is 2, root 9 is 3, anything between root 4 and root 9 is more than 2, less than 3, right. So, 3 minus root 5 therefore, is more than 0, but less than 1. Right. So, therefore, what is I 2 minus 1? What is this integer portion? 3 minus root 5 is more than 0, less than 1. 3 minus root 5 whole power n is also going to be more than 0, less than 1. So, what is the integer part? The integer part is nothing but 0. So, the entire fractional part is 1 minus f, right, 1 minus f. The entire fractional part is nothing but 3 minus root 5 whole power n. So, this is the biggest observation over here. All right. So, 3 minus root 5 whole power n is therefore 1 minus f. This is a very important deduction and this will give you the answer. So, let us go back where I was doing this. 3 plus root 5 whole power n is rho plus sigma, which is I plus f. 3 minus root 5 whole power n is rho minus sigma, and this is nothing but 1 minus f, because the integer part is 0, right. Now, you add and subtract. You add equation 1 to equation 2, you get 2 times rho is equal to I plus 1, and therefore, rho is equal to I plus 1 by 2. You subtract 2 out of 1, you get I plus f minus 1 plus f. So, I plus 2 f minus 1, and that is equal to 2 sigma, which means sigma is I plus 2 f minus 1 by 2. All right. So, what is our biggest observation here? Our biggest revelation. So, I have got 2 revelations. First of all, if I have 3 plus root 5 whole power n, and that has an integer part I and a fractional part f, then I look at 3 minus root 5 whole power n, right. The integer part, whatever it is, the fractional part will be 1 minus f. This is my observation 1. The second observation is that 3 minus root 5 is a number between 0 and 1, which means that if I take it to the power n, it is also going to be within 0 and 1, which means that this integer part is nothing but 0, there is nothing there, all I have is 1 minus f. Okay. So, 3 minus root 5 whole power n itself is the fractional part, which is 1 minus f. All right, let us do another one. Okay. This is the next question. 7 plus 4 root 3 whole power n, that has an integral part I and a fractional part small f, and you have to show that 1 minus f times I plus f is equal to 1. And look at this 1 minus f, very similar in structure, right. So, you know 7 plus 4 root 3, what is 7 minus 4 root 3? Whole power n, that will also have an integer part and a fractional part. Now, let us not think about the integer part right now. The fractional part of this will be 1 minus the fractional part of the original. So, if the original is f, then the fractional part of this is 1 minus f. Okay. And what is the integer part? So, 7 minus 4 root 3, root 3 is like 1.7, 1.732, right. So, 4 times 1.7 is how much is that? 6.8, right. So, 7 minus root 3 is 7 minus 6.8. So, clearly it is something like something less than 0.2. Okay. So, it is less than 0.2, that to the power n is certainly going to be less than 1, which means that the integer part of this is nothing but 0, which means 7 minus 4 root 3 whole power n is equal to 1 minus f. All right. So, if that is the case, if 7 minus 4 root 3 is equal to 1 minus f. So, this is 7 minus 4 root 3, this is 7 plus 4 root 3 whole power n. So, okay. And what have I got? 7 times 7 and 4 root 3 times 4 root 3. So, 49 minus 16 into 3, so 48. Okay, you have got your answer. Fine. So, this was easy. Once you get the hang of it, it is all really easy. Let us try another one. So, let us say the question is p is equal to 2 plus root 3 whole power 5, and this p has an integer part and a fractional part. F is the fractional part. So, the way the question can be stated is f is equal to p minus the largest integer inside p. Okay. This is given. Find f squared by 1 minus f. Okay. So, this is the question. Find the value of f squared by 1 minus f. How do we do this? So, once again I look at 2 plus root 3 whole power 5, right. It is going to break up into some integer terms, some fractional terms. The fractional terms are all related to root 3, right. If I look at 2 minus root 3 whole power 5, then I will get the same integer terms and the same root 3 terms, but the root 3 terms are all going to come with a negative sign, which means that the fractional term in this is nothing but 1 minus f. All right. Then what about the integer term? There is an integer term 2 minus root 3 is 1.732, right. So, 2 minus root 3 is less than 1, 0.26 something. So, that whole to the power 5 is certainly going to be less than 1, which means that the integer term is 0, which means that all you have is the fractional term. So, 2 minus root 3 whole power 5 is nothing but is equal to 1 minus f, where f is the fractional part of p. All right. So, this is what I have. So, then what is f? Okay. And then you have to find f squared by 1 minus f. F squared is 1 minus 2 minus root 3 whole power 5 the whole squared, and 1 minus f is nothing but 2 minus root 3 whole power 5. All right. And then what are you going to do? How will you solve this? How will you work this out? You have to rationalize it, right. So, you multiply numerator and denominator by 2 plus root 3 whole power 5. Okay. And 2 plus root 3 times 2 minus root 3 is 4 minus 3, which is 1, 1 whole power 5 is 1. So, this whole thing is just 1. So, you do not have to worry about the denominator, and in the numerator you have got 2 plus root 3 whole power 5 into 1 minus 2 into 2 plus root 3 whole power 5 into 2 minus root 3 whole power 5, and then plus 2 plus root 3 whole power 5 into 2 minus root 3 whole power 10. But you already know that 2 plus root 3 times 2 minus root 3 is 1. So, 2 plus root 3 times 2 minus root 3 whole power 5 is 1, correct. So, 2 plus root 3 whole power 5 and 2 minus root 3 whole power 5 will cancel out. So, this is what will remain. All right. And how will you expand this out? All the odd terms, this has positive odd terms and this will have the same odd terms, but negative. So, the odd terms do not even have to be considered, only the even terms matter. If you look at these two, only the even terms need to be accounted for. So, the even term here is 2 power 5, right, into 2, right. Let us not write it twice, I will just write a 2 into. Then the next one 2 power 4 will cancel out, right. Then the next one is 2 cube and 5c 2, right. What is 5c2? 5c2 is 10. And root 3 squared, right, and 2 times that. Then the third term again will cancel out because it is root 3 cube, right, we do not worry about it. The fourth term matters. What is going to be the fourth term? The fourth term is going to be 2 times two times 5c4, right, 5c4 is 5 and root 3 whole power 4, which is 9. Okay, and then the fifth term is root 3 power 5 minus root 3 power 5, they will cancel out. So, you do not have to work with the fifth term, this whole thing minus 2. So, 2 power 5 is what? 32, 8 fours are 24, 240, and this is 90. and then what is it, 272, 362. All right. Not doing it this way would have made you run around in huge circles. So, this problem would have been extremely complicated if you had not done it this way, if you had thought of some other complicated method. Okay. Want to do another variety of problems? Sure. So, you are given an equation x power 2001 plus half minus x whole to the power 2001 is equal to 0. Okay. If you have an equation which is like this, right, it is a polynomial. Once you manage to expand this, I can't expand this, right, but someone who can expand this will find that it is a polynomial of order 2001. Right, and that is equal to 0 means that it is going to have how many roots, how many solutions will it have? It will have 2001 solutions. Okay. Now, not all these solutions are going to be real, some solutions are going to be real, some other solutions are going to be complex numbers. Okay. But the big question over here is find the sum of the roots. Right. So, which one is real, which one is complex is irrelevant, we have to find the sum, the sigma of all of these roots and figure out what its value is. Okay. How do we do this? Now, imagine all these roots individually, right. So, let us say that these roots are P1, P2 and so on, P3 all the way till P2001. Right. Suppose these are the roots, then this entire expression can possibly be rewritten as x minus P1 times x minus P2 times x minus P3 all the way till x minus P2001 is equal to 0. Is this reasonable? Maybe, right, maybe not, we have to check the power of x to the power 2001 in this, but maybe this is reasonable. Okay. So, a quick check shows that this is unreasonable. Why? Because x power 2001 does not really appear. No, it does, it appears. So, this is reasonable, but there is going to be some factor over here, right. So, you have to pick a factor. No, this is unreasonable, you do not get 2001 roots at all. So, this will expand into a lot of terms, half to the power 2001 plus etc., all the way till x to the power 2001, and that will have a minus sign, that minus x to the power 2001 is going to cancel out with plus x to the power 2001. The net result is going to be that this is not going to be a polynomial of order 2001, it is going to be a polynomial of the order 2000. Okay. So, if it is a polynomial of order 2000, then it has only 2000 roots, in which case this is not going to appear. The last term you will see is x minus P 2000, right. For the 2000th term, what will you get? You will get x to the power 2000 minus x whole to the power 2000, which is a plus, and you will get a half, right. So, when it comes to x to the power 2000, the coefficient is going to be half. If you expand this expression, the coefficient should match, which means you should have a half over here. All right. Now, this is another way of writing the same story. That is what I am declaring. So, I am declaring that x power 2001 plus half of half minus x whole power 2001, this whole thing is equal to half times x minus p 1 times x minus p 2 all the way till x minus p 2000, okay, where p 1, p 2, p 3 all of these are the roots of the polynomial. Okay. So, what do we do over here? One thing you can do is you can try to expand this out, and when you try to expand this out, the first term, so first of all you have got x power 2000, right, that is by construction, and then you have got x power 1999 times p 2000 times p 1999 and so on, all of them. Okay. So, the sum of the roots times x power 1999, right. So, the coefficient of x power 1999 in this expansion is the sum of the roots. All right. So, all you now have to do is find out the coefficient of x power 1999. And what is that going to be? 2001 choose 2. All right. So, what is your final answer? Your final answer is sigma pi is equal to 2001 choose 2, which is nothing but 2001 into 2000 by 2. All right. So, we have done quite a large variety of problems, and we can do a few more problems in the next class. These are all variants of the binomial theorem. You might not be seeing the theorem in action directly every time, but what are you doing every time? You are choosing a few terms, not choosing some terms, choosing some terms and rearranging the exponent. So, let us stop here, and I will see you soon. Thank you.